Dear participants, our esteemed speaker will be joining us within 5 minutes. We kindly request you do not leave this meeting and stay connected.
डॉक्टर रोहित सर ने ज्वाइन कर लिया है, आपको होस्ट बनाइए उनको। डॉक्टर साहब नमस्कार। प्रकाश सर, आप मुझे सुन पा रहे हैं? प्रकाश सर, आप मुझे सुन पा रहे हैं? गंगा सेठी सर, आप मुझे सुन पा रहे हैं? सर, आपकी आवाज मुझे नहीं आ रही। आप रिज्वाइन करिए, एक बार एग्जिट कर जाइए, फिर रिज्वाइन करिए। आप एक बार लॉग आउट करके फिर आइए। आप आपकी आवाज नहीं आ रही है सर। रोहित को होस्ट बना देना सर को।
यस सर। हेलो।
हाँ डॉक्टर साहब नमस्कार।
नमस्कार अंकुर भाई, अभी अच्छा है।
हाँ बस बढ़िया, आप प्लीज पीपीटी शेयर करिए।
एक मिनट है।
सर अगर पीपीटी में कोई दिक्कत आ रही हो तो हम अपने थ्रू उसको कर सकते हैं प्रेजेंट। प्रकाश सर, यदि पीपीटी प्रेजेंट करने में कोई दिक्कत आ रही हो तो हम प्रेजेंट कर सकते हैं उसको।
वो उधर से।
हाँ उधर से आप मुझे पीपीटी व्हाट्सएप या मेल कर दो।
ओके ओके, एक मिनट। अभी देखो, आ रहा है क्या?
नहीं आ रहा सर।
नहीं आ रहा है ना?
नहीं आ रहा।
एक, मैं व्हाट्सएप में भेज रहा हूँ, देखो आपको। हाँ, शेयर।
Yes, Doctor Saab, it's visible.
अभी ठीक है?
हाँ ठीक है डॉक्टर साहब, ठीक है।
Yeah, please go
डॉक्टर
ahead.
रेवांगिनी, डॉक्टर रेवांगिनी।
Yes, sir. Sir, am I visible and audible?
Yes, sir.
यस परफेक्टली।
Okay, sir. Thank you, sir. So, shall I start?
यस
Yeah.
प्लीज प्लीज।
Okay, sir. When research meets innovation and dedication meets purpose, agriculture becomes the driving force for sustainable future. Namaskar to one and all present here. I am Dr. Evangini Ranjha, Director HR and Academics, AgriMeet Foundation Bharat. And it gives me immense pleasure to welcome you all to day 23 of Ankuran 2026. On behalf of AgriMeet Foundation Bharat, under the visionary leadership of our respected Chief Secretary and Course Director, Dr. Ankur Sharma sir, I extend a warm and heartfelt welcome to all the participants and our esteemed keynote speaker, Dr. Prakash Ganga Shetty sir. Dr. Ganga Shetty sir is currently serving as a senior scientist at CGIAR, ICRISAT, Hyderabad, India. He completed his PhD in genetics and plant breeding jointly from the University of Agricultural Science, Dhariwal, India, and the University of Wales, United Kingdom. Over the past 13 years, he has built an outstanding international career in crop improvement, working across India, West Africa, Nigeria, and the United Kingdom, making significant contributions to the global agricultural research. His scientific achievements are truly remarkable. Sir has led several world first innovations, including Africa's first iron biofortified pearl millet variety, the first single cross pearl millet hybrid, the world's first speed breeding and seed chipping protocol in pigeon pea, and the world's first double haploid protocol in pigeon pea. His research continues to break through in climate resilient and nutritionally enriched crop improvement. A globally recognized scientist, Sir has received numerous prestigious honors, including the Bayer Ted Crosby Beecher Burlock International Impact Award, the IPCC Fellowship, the Promising Young Scientist Award, and the Best Seed Scientist Award, among several other international recognitions. Beyond his research excellence, he is a passionate mentor who has successfully guided 14 PhD scholars, 7 master students, and 10 postdoctoral fellows, while leading several multi-million dollar international research projects aimed at enhancing food security and improving farmers' livelihood across Asia and Africa. Dear participants, today's session offers a unique opportunity to learn from a globally acclaimed scientist whose work is transforming pulse breeding through cutting edge genetics, genomics, and innovative breeding technologies. I am confident that his insights will inspire all of us to think beyond conventional approaches and contribute meaningfully to the future of agriculture. Now, without taking much of your valuable time, I humbly request Dr. Ganga Shetty sir to kindly address the gathering and enlighten us with his valuable insights. Sir, the virtual platform is all yours. Please.
Yeah. Thank you. Good evening, all the participants and colleagues who joined here. Apologies for my delay in connecting to this presentation. So I'll be presenting, thank you. I'll be presenting especially on AI-assisted genomic selection in pigeon pea to deliver higher genetic gains in the semi-arid tropics of Asia and Africa. So my topic will be based on our experience and the current work on the pigeon pea we are doing for both Asia and Africa here for the today's participant. And many thanks to Ankur and his team for inviting me for giving this presentation. So let me start with some basic introduction about my topic actually. So you all know pigeon pea are the arahar dal or dal which we eat every day in India. Specifically, it is one of the most important dal as part of India's. If you take the consumption in with idli and those kind of things as a sambar. So here, if you take the pigeon pea consumption pattern, so we have the consumption pattern. If you look at into the globally, so yeah, it is consumed as a whole grain around 10 to 20%, and green seed or vegetable and around another 10 to 20%, and pigeon pea flour and fasta it is around 5% in the world. but majorly it is consumed as a split seed without coat. That is called as a dal. So if you take overall consumption in the world, it will be around 60 to 70% consumed as dal and another 40% as a whole grain and vegetable pigeon pea. So based on this consumption pattern only, we designed our breeding program, especially for Asian population around the world. We will breed them for dal varieties, and for the whole grain and vegetable consumption, we specifically breed for African continent and also for some of part of the American, South American countries, and also the Australian, some of the continents. So this is how the pigeon pea consumed around the world. And if you take the specifically the crop cultivation status globally and in India, globally India is the major producer of pigeon pea, around 4.4 million hectares, with a production of around 3.67 million ton, with average productivity of around 824 kg per hectare. And globally it is grown in around 6.35 million hectare, around 5.47 million tons is the global production, and on an average globally it is around 861 kg per hectare. So if you see, the average productivity of this crop is very low, around 850 60 kg per hectare. But if you take the Indian population and the consumption pattern, although we produce around 3.6 to around 4 million tons of pigeon pea, but the problem is we also import lot of pigeon pea from outside countries, almost around in 2023 worth of around $633 million. And if you take the year-wise pulse importation, especially when it come to pigeon pea, I will present in my next slide. These are the countries around the world where the pigeon pea grows in around more than whatever the 6-7 million hectare, specifically Asia and Southeast Asia, some countries in Southeast Asia like Philippines and Myanmar, and in Africa, especially in Uganda, Kenya, Tanzania, Malawi, Mozambique, and Ethiopia, up to Sudan, they grow pigeon pea there. And when you come to South American countries, especially Colombia, Venezuela, Peru, and these countries, the pigeon pea grows more happily in compared to other countries. So this is the production in million tons. Again, India is the major producer, and some of the importation comes from our African countries. So this is yield kg per hectare. If you see the highest yield, it is in Peru, more than 2000 kg per hectare they are taking. And another in East African countries is almost around 1000 kg per hectare to around 1500 kg per hectare. And India, we are just lagging behind the more production. Even if you see, Philippines is having more productivity than India compared to other countries. And in India, we are on an average of around 500 to 1000 kg per hectare, average around 860 kg per hectare. So this is the pigeon pea importation trends in India from 2015 to 23. Again, you see the increase in trend of importation of pigeon pea, specifically because of the in some of the inherent problems within India. And now we are the not only country which import pigeon pea, but there are several countries in the world, like India imports almost around 834. This year it has reached already $1,000 million worth of pigeon pea importation to India. And second biggest importer is United Arab Emirates, around 15 to 16 million million worth of USD. And United States again 15 million, and Nepal is around 11.4, although it is very neighbor to our country, but they also import pigeon pea worth of $11 million. Like other countries also, they import pigeon pea. So this is how the major importance of pigeon pea there in India. That's why we have now the called as Atmanirbharta in pulses, or the pulse mission in India, to curb this importation and also produce more locally and consume within India itself. So for producing more pigeon pea within India, Government of India along with the CRISAT and IIPR Kanpur and all our ICR team has developed some major things to develop, improve the pigeon pea production in India. So for that, there are two major theories actually: vertical expansion of pigeon pea and the horizontal expansion. Vertical expansion is to improve the production and productivity within the rainy season, and horizontal expansion is to expand the area of pigeon pea post rainy and summer agroecology. So in these two directions specifically, we are working for benefiting our farmers and helping us to produce more pigeon pea within India. Specifically, vertical expansion is the introduction of new early maturing disease resistant pigeon pea varieties and also hybrids in the rainy season. and also bringing them to off season for production and also increase the area under PGNP. Then population of good agriculture practice demonstrations, then distribution of seeds which are in advanced stage 2 so that the farmers can adopt the high yielding varieties as soon as possible. Then improved farm implements and mechanization and also the processing units to reduce post harvest losses, then capacity building of farmers and those kind of thing. Then increase the seed replacement rate and also promotion of micro irrigation and micronutrient IPM and INM practices. And for horizontal expansion, specifically, we are bringing additional area of PGNP that is specifically under non-traditional areas and low productive districts within India, and intercropping of PGNP with other crops wherever possible to improve the production. And PGNP newly completed big irrigation project where we are bidding for PGNPs for irrigated agroecologies with very high yields and PGNP in the rice fallows. So these are the two major expansion of PGNP areas into vertical and horizontal expansion. And most of you know already ICRISAT is working on PGNP from almost around 55 years now. And globally, we have released in around 135 varieties and 2 hybrids from ICRISAT bred PGNP material and in around 19 countries. So majorly these are the countries where major PGNP grows, and these are the varieties released by the ICRISAT. So some major important milestones for the ICRISAT breeding program is ICRISAT is the one who introduced the lot of pigeon pea from around the world into India and other countries. And we are the one specifically in collaboration with ICR and also NORS program partners release several first varieties for cultivation. Among them, major important breakthrough happened for sequencing of pigeon pea in 2011. Then high density arrays developed in 2018, and 2023 major funding got from Government of India to enhance pigeon pea production and bringing early maturing pigeon pea varieties with many state and central sponsored project. And in another very important breakthrough is in 2024 where we have developed the world's first pigeon pea breeding protocol. And in major breakthrough again happened in 1991. That's the world first pigeon pea hybrid GMS hybrid developed. And in 2008, the commercial CMS hybrid has been released from the ICRISAT bred material. So these are some of the breakthroughs happened in ICRISAT breeding material. So, but the major challenge still was limiting was the, if you see the breeding programs across the pigeon pea around the world, specifically because of its highly photosensitive and thermosensitive nature, and the maturity group is almost very much variable within the crop, like 90 days to 180 days and up to 240 300 days maturity groups are also available. So if specifically breeding those, what happened is it takes a lot of time to breed these particular varieties, like breeding cycle itself like around 1 to 7 years, then testing another 2 to 4 years, and release and commercialization takes another 1 to 2 3 years, and again after this release commercialization takes another 3 to 5 years to popularize a particular variety. If you take the overall cycle of conventional breeding procedure, it almost takes around 12 to 13 years to release a variety, then commercial and almost 15 years. And if you see the current climate change pattern, so it can change within a year, and within 2 3 years also major changes will happen. But our slow pace of breeding always hampered developing the new varieties with the trait which we required in the market. So for that, what we did is actually we introduced some of the new technologies to accelerate the genetic gain by introducing like RGA, that is the rapid generation advancement, where earlier we used to take one generation, now we can take up to 3 to 4 generation. And another important thing like use of molecular tools for diversity analysis, marker for defensive traits, and marker for fertility, and genomic acid selection, then whole genome resequence panel, and also we are now editing the gene editing process is also going on. And major important also we brought on precision phenotyping of some of the traits which we breed in current breeding program. Then analytical power. So after you have the RGA rapid cycle genomic selection, then we have all the both RGA and molecular tools, and also we have precision phenotyping. Then using all of this along with the analytical tools like advanced statistical tool to improve our germplasm to breed them stable genotype across the multi-environmental environments. So these are the new tools and technologies we introduce in Pigeon P. If you see my topic also, it is AI assisted genomic selection. So think about how AI can help in our breeding program to enhance the cycle and also bring new varieties within a shortest period of time to the farmers. So this is how we have brought the breeding program. So if I take overall our breeding program, specifically when we how we breed the pigeon pea varieties is like we have segmented our breeding program into market segment. So as I told, the consumption pattern is very most of it goes for split dal. So we breed for split dal varieties for Asia and Southeast Asia, and we put almost around 70% of our entire global breeding effort of Ecrisat goes to breeding split dal varieties. And for vegetable pigeon pea and whole grain consumption, specifically we breed for Eastern Southern Africa and also South American countries, and we put around 30% of our breeding effort to bring the scientifically proven vegetable pigeon pea varieties to the market, specifically for our Eastern Southern Africa and for the South American farmers. So this is how the market segmentation has done for our breeding program. Then these are the ones we done the market segmentation. Then we have the target product profiles to breed for specific varieties within those market segment. For if you take the dal varieties, then we have different durations of varieties, like medium duration, mid early duration, and extra early duration, or the super early duration. And for the tip, specifically for the in as this is the hybrid crop as well, and also we breed the early maturing pigeon pea hybrids in this particularly for pigeon peas. So first three target product profile specifically breed for the varieties, and the fourth target product profile concentrate on breeding the hybrid parents and restore parents along with the commercial hybrids available to the seed industry and also for the farmers. So if we take the what are our target rates for these four target product profile, first is the yield, which goes almost 15% over the best check available in the current breeding pipeline, and also the present cultivar varieties across India, popular varieties. And maturity, like appropriate maturity we take. If you breed for south and central zone, we breed for early maturing varieties. If you breeding for northwestern hilly zone, then we go for medium and long duration varieties. And for the hybrid, we go for the early maturing around less than 150 days varieties. Sorry, less than 150 days maturing hybrids. Then we also have a major disease like wilt and stolty mosaic disease, and recent days we are also getting phytophthora blight. So these are the must-have traits. So in most of our breeding cycle, whatever the line comes, we will have all these traits along with the 100 seed weight. 100 seed weight is very important trait which indirectly correlates with the quality of the dal. So if it is less than around 11 gram, that would be good for the dal millers, and also for the taste of the dal will also not change. So these are the 6 7 must have trait we take care in our breeding program in the breeding cycle. Then we also go for the yield testing at the end of after completion of breeding cycle. So as I told, these are the major challenges in pigeon pea production. So if I specifically put here, we have the 2 season we are planning to produce pigeon pea, that is rainy season and the post rainy season. So in this particular slide, you will be looking for what are the major challenges in the rainy season pigeon pea or the Kharif season. So specifically, as I told, due to heavy rainfall during last 3, 4, 5 years, we have phytophthora blight and the waterlogging became major challenge. Then Maruka in early pigeon pea is the biggest challenge compared to long and medium duration cultivar. And we also have the stolty mosaic disease, drought and heat, and the pod borer and dry root rot are the major challenges in the Kharif season pigeon pea. So in my next slides, I'll be showing how we breed for the Kharif season varieties, and we also breed for the post rainy season varieties. So to breed these varieties, we work with a network of people. This consists of both public and private sector. So we have the Global Pigeon Pea Network to deliver higher genetic gains. It includes almost all the national program partners, ICR, and all the government, state governments which support this particularly network projects. So this is the very recently concluded network project funded from the Government of India, Ministry of Agriculture. So it involves led by Ecrisat in collaboration with IIPR, and also we have involved around 13 state agriculture universities starting from Punjab to Karnataka. So in that our major activities were like enhancing the pigeon pea, that is vertical area, very vertical production, and also the horizontal area expansion. For vertical production, we have taken 6 states: Uttar Pradesh, Madhya Pradesh, Maharashtra, Karnataka, Telangana, Andhra Pradesh. And for horizontal expansion, we specifically went with Punjab, Haryana, Rajasthan, Bihar, Chhattisgarh, and Jharkhand. So these are all our program partners to deliver the best varieties to the market in all these across India. And we have also leading another very important project, which is called as Vision for Adapted Crops and Soil. This is funded from the FCDO from the United Kingdom, wherein we specifically breed the pigeon pea varieties for Kenya, Tanzania, Malawi, Mozambique. So these are our program partners from all the 4-5 countries across our Eastern Southern Africa. And we have one program that is called as Climate Smart Pigeon Pea program, funded from the UKCG Center from the United States again. Herein specifically it connects to two major continents, Asia and Africa. So for Asia, we are doing in specifically India, that is Telangana, then IIPR Kanpur, and we have the Karnataka and also Telangana. And in for Eastern Southern Africa, we are working with Kalru in Kenya, Tari in Tanzania, and Dars in Malawi. Kenya, Tanzania, Malawi. And we also have the CIMIT as one of the another CG center to contribute to this particular project. So whatever my next presentation will happen, next slide will contribute from all the three major programs. One major program for Asia, one major program for Eastern Southern Africa, and another major program which connects between Asia and Africa. So you see the learning happens between all the both the continents where major pigeon pea production happens. So for vertical expansion, as I told, we specifically breed for hybrids. And if anyone here in this today's lecture, any seed industry was there, they will be most interested to hear about what is happening in our hybrid pigeon pea project. So this is also part of our network project which we done. Specifically when we come to hybrid pigeon pea, we have several hybrid release, and the yield advantage is almost around 30 to 50% over the best varieties available in India. So for that, what we did is specifically we developed the target product profile for our seed parents. So I'm not going to tell what happened in our earlier hybrid programs, where we have specifically bred the hybrids in medium and long maturity groups, and currently we are breeding them under the 100 and less than 150 days. So here we also bringing the major breakthroughs by bringing the hybrid traits in this particular pigeon pea. As we know, pigeon pea is also pulse crop and having the clistogamous flowers, which is very amenable to self-pollination. But when you come to hybrid, it should always be a cross-pollinated one, and mostly towards cross-pollination happens. So for that, we have developed the target product profile in our seed parent, specifically when we are breeding our CMS line. If you see the first picture here, it is highly a cross-pollinated kind of flower structure we are breeding. Second one, you can see it is more open. First one is stigma is more exerted. Second one is complete open flower. And also third one, we are breeding a very non-photosensitive, thermosensitive, very high this combining ability, very high seed yield, cold tolerance in the early seedling stage, and open flower and plant height with a certain height of around 100 to 130 centimeter. Then also we are bringing annuality trait, that is synchronous flowering and maturity, and stable cytoplasmic sterility under a various backgrounds. So these are the some of the traits which we are looking in our seed parent. And in our restorer parents also we are looking for again open poring, non-seeds revealing nature, wilt SMDA resistance, high yielding, then annuality, high pollen production, non-determinate growth habit, and plant height of around 130 to 150 centimeter. So 100 to 120 centimeter in female and 130 to 150 centimeter in the male, so that the pollen can be easily moved to the male to female. So this is one of the recent hybrid seed production we have taken during the summer 2025, wherein we introduced the heat tolerance in most of our male and female parent, specifically to take the off-season pigeon production. So this is the major breakthrough happened in the hybrid pigeon pea, where now you can go throughout the year production can be done in our hybrid programs. So next comes is the when we go for our breeding program. As I told, it takes almost 12 to 13 years. So we have specialized in photopid regime for the pigeon pea, specifically to optimize the speed breeding protocol. So for that, in my last year presentation, I presented this one, specifically how we develop this protocol. So in today's presentation, how we use the speed bidding protocol and develop the new varieties, and also using the molecular tools to enhance our current cycle time. So if you see now the number of generations per year, up to early generations, early maturity group, we are almost taking 4 to 5 generation, and late and mid-late varieties, we are taking around 2 to 3 generations with the speed breeding facilities. And if you see the economic benefit, it is very good with the speed breeding facility, wherein no risk of losing the material, and the economic benefit is almost $0.50 per plant when you take in the RGA, compared to around $1.33 in the field. So almost it is half of the field activity, and it is more precise than the field. So after that one, what we did is we also standardizing the protocol for double haploids in pigeon pea. So most of the pulses, this is to our knowledge, this is first of its kind. We started this work, and now, for example, in speed breeding, we are taking 3 to 4, 5 generations, and the double haploid can give within 1 year around six the highly uniform lines. So we just went with the anther culture, and these are some of the stages we are standardized now. So we also have another one which we are also using, the ovule culture for the production. So currently we are just standardize the protocol, and we just going through the some of the lines which we through double haploid production in the at ICRISAT campus here. And soon we are going also to publish this one and made available this protocol to all the program partners who can use this, particularly DH production in pigeon pea. So this is another breakthrough. Earlier years we have done the RG, and now we are going with DH. So we'll see which one is going to have more comfortable and to use is very less cost. And another one I told also, robust phenotyping for the major disease and the biotic and abiotic stresses. That is the one which is very important for the precision breeding in the current era. So for waterlogging, we are using the 10 days waterlogging screening at both stages, seedling and the at 40 to 45 days after sowing. And the seedling stage is around 72 hours of waterlogging. And for the 40 to 45 days after sowing, around 8 days of waterlogging will be done. And we capture 3 tests, specifically percent plant survivability, flowering, pod conversion. And also now this year onwards, we also started the yield when we induce the waterlogging. So these are some of the lines which I identified them as highly resistant to waterlogging, and now currently taking use of these and introducing into our new lines of with the waterlogging tolerance. So second one is the Phytophthora blight. We have standardized the phenotyping protocol within the lab, and we screen almost around 3,000 to 5,000 lines within a very short period of time, around 15 days. And these are some of the lines which are resistant to Phytophthora blight. If you see most of the lines which are waterlogging tolerant are also resistant to Phytophthora blight. So those one we are using, and for both waterlogging and the Phytophthora blight. So for this is the robust phenotyping, and another one very important thing is the genotyping platforms. So now we have the speed breeding, we have the DH, we also have the precision phenotyping. Now we also have the genotyping platforms, like we have the low density array, mid density array, and we also have the trait linked markers available. And this is called as mid density panel with 2000 markers, with most of the trait markers also included in this one. And if you screen any of your line with mid density, it specifically gives the genome specific signature, and also it can be used for the genomic selections actually. So with this one, all what exactly we did is we started using the genomic selection. As I told, for genomic selection, some of the requirements are there, like training population, genome-wide phenotyping, and phenotyping data are very, very important. And we also have robust statistical tool to analyze them. So here specifically we do variety testing, then select based on the genomic estimated breeding values. Then you use them genomic selection for parental selection, and also for the taking line into further testing process. So here specifically training population with genotype and phenotype, genome-wide marker data, high quality phenotyping, prediction models are GBLUP, ML, AI1, rapid generation, advancement specialty, and breeder plus data analysis capacity. So these are some of the basic requirement for the GS. So my today's topic is also on AI GS actually. So first let us see how GS we implement, then we go to the AI GS actually. So for the GS, these are the major important, and in my previous slides you must have seen so how we phenotype, genotype, then we have the genotypic tools and the breeder and data analytic tools available. So with the involvement of network from Asia, Africa, and also from Australia and other countries, what we did, we started our genomic selection. So we use 4-step model actually. If you see the first one, that multi-location and multi-environmental phenotyping stage in the beginning of that one, that we do with all our program partners in collaboration with ICR. Then second one, we do the genotyping of stage 1 trials, that whatever the multi-location trial we do for building a dynamic training set and training genomic selection model. Then we also implementing the multi-trait GS, keeping in mind the GY interaction in the, as Pigeon Pea is highly GY interactive crop. So we use this multi-trait GS model. Then fourth one is the parent selection. So fourth one is around parents, sorry. So fourth one is about the parental selection based on the genomic estimated breeding values for better heterosis and also for the better yielding varieties for the within a shorter period of time. So this is the 4-step model we are using currently for the pigeon pea breeding. And once we have the 4-step model established, then we develop the breeding scheme specifically to implement rapid cycle genomic selection in pigeon pea actually. So wherein if you take the rapid, how do we do rapid cycle genomic selection? We use around 40 to 50 crosses. This is a model actually, but now we are using more than 200 to 250 crosses per season. Then first 3 stages will go to RGA, and then it will go for direct field selection using the genomic estimated breeding value selection once we done the genomic estimated breeding value in this cross. Then we also, if any best varieties available from the stage 1 with the GUBs, that will go to stage 2 trialing. So if you see the overall cycle in this one, majorly if you see take the year 1, year 2, year 3, earlier it used to take around 7 to 8 years actually. But 7 to 8 years as a breeding cycle and another 3-4 years for the testing cycle. So here within the testing cycle including, it is only 3 years now. So almost we reduced how many years from 12 to 13 years to now almost around 3 to 4 years. Even if we miss any season, it can go up to 4 years actually. Then how we did testing is this is the what AICRP zoning system in India. Specifically, as I told in my beginning slide itself, the target product profiles and the zones we test them. For central and south zone, if we take the area is almost around 85%, where we test almost our target product profile 1, 2, and 4 material. And in first 3 we use, it is almost around 15% of the pigeon pea area is there. There mostly it will go for TPP2 and 4 material, then TPP3. So this is how the phenotyping goes across India in different ACRIP centers. And also we have got the like multi-environmental testing we do with in very close collaboration with AICRP and Curry Pulses across the different zones and also the ACRIP centers in India using this particular model. So we from last product testing and release, if we take the overall product testing, how many we have done and how many we are doing it in the current actually. From 22 to 25 now, or you see the line tested in stage 1 increased from 141 entries to around 500 in 2025 using our partnership model. And number of location tested, you see in 2022 it was 52 and in 25 it is almost around 110. And in 26 it is more than the 110 now. And number of lines which tested from the IVTs goes to the AVTs actually, IVT and IST of ACRIP pigeon pea. So in 22 it was 3 and now 22 we have 52. Then number of lines in they will move to the ACRIP AVT2. It will like 1, 3, 5, 9. So it is in the increasing trend. But the number of varieties released in 23 was 1. In 24 we did not got any varieties released. 25 also we have got 3 varieties released. And again 3 varieties in 26, 25, 26 we have released another 3 varieties. Like this, we use the product testing and release model and systematically involve the breeding process using this particular data from our program partners. And for phenotypic details, we use specifically the soil data from different locations. Then different locations like these are the zones and also testing location from different one. So for specifically phenotyping, you see the numbers of lines we choose for precision phenotyping is goes more than 3,200, 4,000, 5,000 lines like that one. So once we take the data from all the location, we correlate with the phenotypic correlation of across the locations, across the zone, then we identify the zones which are having similar condition and we differentiate them with different, then we strategize our testing program next year. So if they're really different, then we go for more number of testing environments within that zone. So this is the genomic collection matrix which we use across the different lines which use for testing in 22, 23, 24. See the lines which are very much diverse within those selected lines for the testing. So these are the genomic prediction for yield per hectare. If you see the zone, Akola zone, Patancheru zone, we have more than 0.5%. If you take across all the zones, it is around more than 5%. So that we are getting good genomic accuracies. So this is how we implement the genomic prediction model in our current breeding cycle for varieties and hybrids using those model for the Kharif season. For this specifically this to improve for the vertical expansion of the pigeon pea. Then for the horizontal area expansion, specifically we go for the post-training production. So post-training, these are the major challenges like photoperiod sensitivity and agronomic dwarfing. Then seed shriveling, cold tolerance at the seedling stage because we are planting them in Rabi, and heat tolerance because once we are harvesting, it will go to the heat stages actually. Then we have that problem. So these are the major traits which we taken care in the horizontal area expansion strategies traits into our breeding pipeline. So for seed shriveling, there were no protocols available earlier. We standardized the breeding protocol for the seed shriveling. Then we also have the standardized and tested the protocol for cold tolerance at the early stages in Jharkhand, Chhattisgarh, Bihar during the winter season, where we temperature came across 10 to 15 degrees centigrade and classified the genotypes based on the seedling cold tolerance. Then for the flowering stage, the cold tolerance, we tested some of these lines in the Kashmir Valley. And these of them also tested in Chhattisgarh, Bihar, Jharkhand, Odisha in the rice fallow environment to identify the best suitable varieties for the rice fallow environments. And we came with this specific line for cold tolerant pigeon pea in rice fallows of Odisha. And almost it gives very high yield under the uh, uh, rice fallow environments actually. Then we also went with heat tolerance in pigeon pea. Specifically, if you see the ICRISAT's recent advancement of breeding for heat tolerant pigeon pea, we started this program in 2022 and we came with a variety which is very high yielding under the high heat conditions up to 43 to 45 degrees centigrade. If you see the statistics here in 22 we have 40 lines and in 25 it is around 5,000 lines. In 26 I think we have tested around 50 to 60,000 lines in multi-environmental conditions for the heat tolerance. So how heat tolerance we define specifically early maturity, photoinsensitive, thermoinsensitive, 100% pollen fertility under high heat conditions. Then also have the up to 85% pod conversion rate and 100 seed weight not affected one, and annuality and reduced seed swelling. See the lines how they segregate for the heat tolerance under the. You can see the left line which is flowering, the middle line it is not at all flowering, and again the line which I'm seeing the cursor, you see the height but no flowering at all. So this is how we are differentiating the lines and breeding more early maturing varieties under the high heat condition. This is the one summer 25 tested in RARS Warangal where temperature goes more than 43, 45 degrees centigrade. Then RARS Vijaypura, there also we have the high heat. And then we also tested and confirmed these particular lines in ICBA Dubai for the heat tolerance where temperature goes beyond 46, 47 like that one under high heat condition. So now we came up with a specific pigeon pea variety which can mature within 120 days and 40 to 45 degree centigrade tolerance, and first tested in Karnataka, and this year we tested across almost all the states in India. And this is our Honorable Director General, Dr. Himanshu Pathak, who unveiled this particular variety 25444 for the this is not at all not at release, but this is a line which is having a very high heat tolerance that can be further used to breed heat tolerant varieties in India, specifically to improve our horizontal area expansion. So this has a high opportunity for horizontal area expansion, specifically in summer irrigated ecologies with wherever water and irrigation available during the summer. So the summary which I reported here for both rainy and post-rainy season, the speed breeding wherein we reduce 7 to 4 years, and speed breeding plus rapid cycle genomic selection it reduced from 4 to 2 years, and cross to cultivar to 5 years from 13 years, which includes accurate testing as well. So like breeding cycle 2 years, testing cycle 3 years, release and notification, then new variety comes within a 5 years. So almost if you see 60% of the time reduced from the current previous breeding cycle to the current breeding cycle. So still we want to reduce, then we are starting another particular thing called a GS model development for with the AI uses actually. So yeah, what are the some of the constraint in GS model is the training population size and representativeness of the lands, then prediction accuracy across breeding cycle, then non-additive effects, then low robustness when high G by interaction comes, and high requirement for accurate and multi-environment phenotyping in the beginning stage, then market density and LD assumption may not hold across population, then cost and infrastructure constraint for large scale implementation. So these are some of the constraints of the GS. So we went with developing the AIGS model wherein it rapidly predict the genetic merit of the breeding land, and it uses genotype, phenotype and environmental data which we collected from last 5 years now. Then we uses the DNA marker data, phenotypic data, AI genomics algorithm to predict. Then uses but measure importantly, it uses the DNA marker, historical phenotypes, AI models, and random like different models of AI, then predict the genomic estimated breeding value for the untested lines. So how it is very important is that one, if you use them in very early stages, and you can well before the informed lines and replicated yield as trials are available, you can predict that line yield and their worthiness to test further. If we see the concentrating land and labor on high potential lines while accelerating cycle through faster advancement and parent recycling, so it drives a quicker genetic gain under the very tight budgeting as well. So if you have the constraint of the budget also, it can very good, very use it. So for pigeon pea, we are using target like yield and yield stability, heat and drought tolerance, pygidium wilt and stulty mosaic disease resistance, and early maturity. So these are the stump traits we are selecting through AI in pigeon pea. So these are the AI powered genomic predictions model developed actually. So if you see the normal GS selection where you use the RR block and we use the AI selected model, and we tested across different locations. And in our file study, what we found across the 8 environment that AI model consistently outperformed in environments where RR block struggled to. If you see the green lines here, if you see some of the locations in location at the RR blood could not differentiate, but the AI model is the one, it is a little bit better than the RR block model. So that's why this AI powered genomic predictions looking more advanced and also uh, good looking good at the present, and we have to see how this happens in the next breeding cycle. So these are some of the parameter we use for RR block, that is GS model and the AI model, wherein different genotyping density requirement, architecture capital, like genetic architecture captured in our GS model is moderate, but in AI model is very high here. So epistasis also in GS model it is none, but in AI model it is indirect, it capturing. Then prediction accuracy is good in GS model, but high to excellent in the AI models. So like this is a new model we developed, and we will come in the next year to see how this particular model works actually. So this is very important for future crop breeding, where you can use the prediction for all the pan genetics, like whatever the lines which you stored in our gene bank. So you can predict them and use them for your breeding process to develop very high good lines which can be like very high in yield, and whatever the trait we want you can breed within shorter period of time. And also we are using the Google's alpha genome for regulatory variant prediction along with this AI model. So currently this is also we are exploring how we should use in this one. And AIGS can also breed it can cut nearly 50% using genomic prediction model, reduces cost for release variety through targeted testing, and directly benefits smallholder farmers in stress-prone regions, so that we are involving some of them, those things actually. And more climate resilient varieties within a shorter period of time can be developed. So support in decision making beyond selection, AI genomic selection, breeder decision, and high probability of success. And AIGS highlights which environments are most informative for the phenotyping. So these are some of the advantages with the genomic selection models. So the best one is if you take the breeding cycle length, it is 1.5 to 2 years in AIGS plus DH, and AIGS is only 4 to 6 years, and predictive breeding around 6 to 8 years actually. Selection intensity is very good in model. And if you take the genetic gain for year is almost around 3 to 5x higher than the normal one. So this is how the very advantage of the AIGS web. These are some of the platforms freely available one can use for developing these models. The challenges with AI implementation is the black box problem. Unlike traditional statistical model, deep learning models are often non-interpretable. Breeder may see a very high prediction score but want to know which specific genes caused it. So have to study on that one. Then data quality and quantity, AI models are data hungry, which we need very high data in them. Then computational cost in the beginning is very high. And the curse of dimensionality, managing millions of DNA marker relative to small number of physically tested plant can lead to overfitting, where the AI memorizes the data rather than learning to predict it. So these kind of things we need to take care in the breeding program. But the opportunities like multi-omics integration, then personalized crops like AI genome enable can be used for niche breeding to specific local market. Then climate adoption like enviromics and autonomous breeding can be used through this particular AI's model. So these are where our program partners and the donors for particularly our current work. We must thank all of them for funding this kind of work for breeding, bringing new pigeon pea varieties to the Asia and Africa. So thank you. Ankur?
Thank you so much, sir. Thank you, sir, for such an insightful lecture. We shall now move on to the interactive section. Dear participants, this is an excellent opportunity to interact directly with our esteemed speaker. If you have any questions or queries, kindly feel free to unmute yourself and ask them directly. Alternatively, you may post your questions in the chat box and I will be happy to read them out on your behalf. We encourage every participant to make the most of this valuable opportunity.
Hello?
Yes, sir.
Yeah, sorry, my laptop got disconnected because of low charger.
No problem, sir.
Yeah, we can take some questions.
Yes, sir. Yes, sir.
Yeah, please go ahead.
The participants are appreciating your lecture in
Yeah,
the chat box.
thank you.
So we believe that your lecture was so comprehensive and self-explanatory that the participants are unable to come up with any questions at the moment.
Okay.
So I believe that we can conclude this session.
Yeah.
So as we come to the close of today's enlightening session, I would like to express my heartfelt gratitude to our esteemed speaker, Dr. Prakash Gangashite sir, for delivering such an inspiring and knowledge-rich lecture. Sir, your valuable insights, vast international experience, and remarkable contribution to crop improvement and global agricultural research have made today's session truly memorable. On behalf of AgriMeet Foundation Bharat and the entire organizing team, I extend our sincere appreciation for your valuable time and for your graciously sharing your expertise with all of us. I would also like to thank all the participants for their presence in today's lecture. With this, I, Dr. Evangini Ranjha formally conclude today's session. Thank you, sir. Thank you, everyone, and have a wonderful evening ahead. Thank you.
Thank you so much, Daksha.
Thank you, Ankur bhai.
Thank you. Good night, sir.
Good night, bhai.